try to understand that what is the because as I see that the different that as I see that the different topics being covered by now is regression, multiple linear regression, logistic regression, and yes, and I think and I think last one, I think random forest probably, that's also being covered. And like if do you want something, so just to, before starting, so what is my assumption I'm considering here is that you got little bit comfortable with the programming R, and you are comfortable with the multiple linear regression, you are comfortable with the logistic regression, and you are comfortable with the train test validation. What you call it is a models. One of the techniques for model selection is the cross validation, and also the train test validation. Also leave one out cross validation. So these three things. Are you comfortable with this? So if you are with this platform R itself, because there are many things nowadays, as most of the things are available online because of the data science projects, lot of online repository, many things are already available. So this is a common tendency for many students is that uh, we take up some case study from the internet itself and try to recreate it and submit possibly as a project. So here let me just try to tell you some of the things, some of the practices that what we are doing and how we are utilizing this particular platform R Studio very effectively. Let me start with my first demonstration. Let us try to see that. I'm just opening up a document. So if you can see this document, say Introduction to Probability Distributions. Because many of you are research scholars and probably many of your faculties teaching in different university and institution or colleges. So for example, these are the documents which often we create uh, for a better understanding of the students how things are working. Say for example, typically when I started teaching in here in ICT Mumbai, so typically we take that, we do the board work, we draw the probability formulas, we write down we have done the formula for the normal distribution. Right? So let me just open up this journal also, because one session is on effective documentation using RStudio as well. So, like typically when you go, we write that x follows normal mu sigma square, and its probability density function is. Unless something is happening, we rarely either we show some kind of fixed graph or something. That is what we show to the students, or copy it from some book. Or if we generate some kind of a document, then we usually create that document in a word processing software and make that and put that image into that software and create it. So let me try to understand if we can have a dynamic documentation. In a sense that today whatever the things I have taught, I included it in the document. And tomorrow I have another requirement. Today I am using normal distribution with different mean. So my PDF is different. If tomorrow I am using probable normal distribution with a different sigma. Say for example, my PDF is going to be more what is called as a flat. So now so every all the work that you have to do it once again. Another thing may be that you are comfortable in Python, but the students are trained in the R programming or some other softwares. Or you are doing your research activities using R programming, but students have a software lab which uses Python. So that means lot of when we are teaching, like a lot of such complications comes up. So what actually we can do, we can effectively utilize this RStudio platform to effectively create the documents. So for example, showing a document which I use for teaching in ICT. So for example, Introduction to Probability Distributions. This is probability density function. So then some continuous distributions, right? Some of the distributions will come. And similarly, how can we compute probabilities? These things. You see that a lot of R codes and Python codes are being embedded here. So if you click on this, say our code, so it is going over here. Of the same thing, if I click say Python code 22, so it will go to this Python code over here. So that means in the same document, I have Python codes also and I have R code also. This is an extraordinary feature that our studio is offering, because nowadays user of both the community has increased significantly. And for our students, half of the students are R user, half the students are Python user, some people are in fact Julia user also. So there are a lot of dynamism is happening in terms of use of softwares. So what we do here actually, so for this is a document, how do we create it? Go over here. So what you can do over here, so you see that there are several options. R script is the basic one where you can make a just regular script, and whole lot of options. You can write your Python script also here. You can write Shiny web application. If time permits, tomorrow I'll show you some demonstration of Shiny web application also. So this is R Markdown. This is the document which you are looking at it. This is being created by R Markdown. So if you click on this is a window it will open. So you see that there are multiple options that is giving up. HTML, PDF, and Word file. So several possible options you can create. So say for example, I can give the name my first markdown, right? So you can give an HTML and press OK. So a new file got created. Okay, so this is the basic demonstration is already here. Some of the things they have added. So you go to KNIT. See, there are different options. Say, for example, you meet with HTML. So you have to save this. Say, let me just save it over here. Right? Say, I'm just creating a new folder. We have to give a name also. Say, let me with the name. So executed it. So it's getting rendered. And this is the file that you have got. So you can open it in browser also. Just click it in open in browser. So this is going to open in browser. So in the same documents you can include plots also, right? So there are headers also you can give, like there are multiple things you can. So this is the most basic part what I have done, what I have shown you. If you follow this process, this is the most basic part you are going to get. The beautiful part of this, that in the same code, in the same file, you can include your codes, you can include your outputs also. So if you write down summary of something else is going to appear. So that means you don't have to do copy paste and everything you don't have to do. And the PDF, that if you do the PDF part of this, say for example in the same file, I'm doing a meet with PDF. So yes, output file, it is been rendered. Yes, it is done. So let me open that folder. Right, this is the PDF file it got generated. This is the PDF how it looks like. So this is the most basic one. So when we start with something, I also started with this example only. So when you plan to start, you can start with the most basic example, and then you try to get into a more and more complex things. So say for example, let me talk about this is the probability distribution which I can see now. Over time, let me open now the file which I have updated over the time for the teaching and research purpose. So you can set your title, you can set your author, you can set your date. Here for some visualization, I just put date over here. I don't want date here. I just put this comment. And then whether you want numbered section, right? You want table of content, you want some subtitle. There are many things you can do. I know you have understood packages as well. So since you know that how to take packages and everything. So for example, this is one package, reticulate. So this package is for Python code inclusion. So in the same file, you can write down these comments as well, right? Right. Then whatever the Python requirement is there, that is something you need to take it over here. So this is the code, as those who are Python comfortable in this. These are the functions from Python. These are the packages, modules from Python that we are going to use in rest of the things. Okay? So now you observe that. So for example, this symbol means that those who are LaTeX user, you can write down begin section as well. So you write out the slash section. But this is the comment slash this read it as a. So if you see that this document, if you open up, so it comes as a header. So this is for a section, right? So similarly, so you can write down this straightforward documents, and you can write down the mathematical expression as well within the dollar symbol. Okay. So then if you can write down this, you can put something in between. You know the LaTeX, those who know about LaTeX. So then you know that this is a begin cases, and in cases, this particular thing is going to give you this one. So once you execute, this thing is going to appear. Now the both of these functions, you want to represent that here. So immediately after that, you want an R code to happen, right? This is an R code, you want it, right? So this is function f, and this is function g, and you want to curve, you want to plot both these functions, right? So let me just check out the code. So this is the code here. Explicitly, I have written, right? So you can, so this as symbol within the R environment, it basically understand it is exclamatory sign, or it is a comment for putting a comment. Now in the same file, the same one, somebody who is a student who does not know what is how to do it in R, but he knows Python. So the same code here we have written as a Python. To understand that Python eval equal to false. That stands for only this code will be visible, the picture will not appear. Only the code will be visible. Say for example, if I open this one, if you see that this is the picture only has appeared, this is an output from the R. However, this is the part which is a Python one, there is no output has printed from here, because we have set it as eval is equal to false. So that means this part of this document will appear in your document, it will appear, but it will not print the output, it will not show the figures. In addition to that, you can write down the figure. So here, for example, for R code, I set eval equal to true. I can give fig caption also, figure caption, right? See that in the, here I wrote the figure caption using integrate function. So if you, right, you can write down that font will come, we will have different font function. The area under these two curves are computed. So fig dot align means you want that figure to be in the center. So for example, let us just check this figure out once again. So okay, this figure seems to be pretty big. So you may want to resize this figure a bit. So let me just resize what we can do. So here you can do it, say fig dot. If you give, there are multiple options, right? Fig dot height. You can give say 3.5. Okay. So this here you are going to get two outputs, two plots will be there. It will be executed and Python will not appear. Now, let me execute this file. Let me execute. Now you have seen already this problem or this file. So let me see what is the revised file is coming up. So now I'm executing this complete file. So here you see that which are the codes are getting executed. So here also it will be visible. It is being rendered. So please understand, I thought of making this one session at least a kind of a live demo so that you understand that people are using it. we are effectively using it for our purpose, and it has significantly reduced our uh, like like manual efforts. So once you have created it, and it's done. So let me see. Okay, let me check out. You see that the figures are now in a better shape, right? So these figures are getting changed. Now note that these figures, so typically what we do, we write a program in our script. The picture got generated usually here. If we write it, here we got the picture. Say for example, plot r norm 100 and r norm 100. All is equal to red. Typically, say for example, this is the plot that we generate typically here. Then we take it and export it, copy or save as PDF, or there are multiple options. You can save it using APS, JPG, PNG, TIFF, DMT, many format it is there. So you do it and you copy it and paste it in your Word file. This complete thing is very difficult, right? So it is a very manual task. So in other words, say for example, tomorrow next year you thought that, okay, I want to change these examples here, not probably this one x cube. I want it to be something, say I want to give x to the power 5 here and 2 to the power minus x cube. So you may want some function over here. Say, let me write down this. Say you want some other function here. Say here it is, I'm writing it. In the document, you can just change it x cube into the x to the power 4 and e to the power minus 2x. This is the function we have written. So x to the power 4 and e to the power minus 2x. Let me make the change here also. E to the power minus 2x into x to the power 4. Let me again execute this document. It will be 2 star x, not only 2x. Let me again execute this document. Yes, it is getting executed. So things are happening live in front of you. So it's not that something I kept it and just for show purpose and you try. No, it is something live. You can very easily do it. Okay, it is done. So let me check out the file now. Say introduction to probability distribution. Let me check out what is happening with that. Yes. See that here gx has become this function and the plot has also changed. This is a very wonderful software and wonderful platform. It provides you wonderful flexibility. Right? That is very important. You can visualize various different shapes of probability distributions, and using the single document, you can show it to the students, and this is how it is working. So for example, this is the normal distribution. So you can write down, you can customize the codes and write down several things. You write down mathematical expressions over here. Similarly, you have the Python code also here, but it is not being executed. So the people who are a Python user, they can also easily connect it. So they can run these codes and execute. So you can have different shapes of normal distributions. So as you see that the sigma as sigma, because typically when I at the initial time I used to explain, okay, sigma is more means your distribution is going to be more flat. And students, it's like Vedvakya and students used to believe it. But nowadays the revolution is happening that with all the softwares, representation, presentation, graphical documentation, that revolution is also happening. So as a researcher, as a teacher, probably it is better we adapt it also. And at least I personally got heavily benefited by this. So for example, if we change our mu, then shift in the distribution is happening. However, there is no change in the variance is happening. But however, as sigma changes, we are going to have as more sigma means the distribution is getting more spread. Sigma is less means I'm going to have a more concentration around the expected value or the mean. Right? So you can have a figure captions also. So similarly, you can have you can include more and more information over here, that what is the and with time the same document, it's not that today I have written a document and it's going to be like last year I have created it. So you see that it is a continuous process. So as things are working, the same document, the same R file, you are actually, I'm actually executing and modifying and improving this document further and further and further. So so these are various probability distributions that you can get, and it is also provide you a table of contents. So easily you can go. Let's say for example connections between distributions. If you click over here, it will take you in this here. So you can make very wonderful visualizations, because at least later when I have studied that, so we learned that binomial distributions, if n is large and p is small, those who are from statistics background, they know that if n large and p is small, then probability distributions for binomial np can be well approximated by a Poisson distribution. And what we do, usually we take a moment generating function approach or characteristic function and try to show that as my n increases and p goes to 0 and np is of moderate range, which is lambda, then the binomial moment generating function is basically acts like a Poisson moment generating function. So these are very common questions for also for the uh, for the undergraduate statistics or postgraduate as well. However, if that never actually made sense to me, I always take it as a mathematical expression only. Here also, when I taught here, I also did the same thing. Then suddenly students are saying that, sir, we understood it, but what is that maths is clear, but we are not able to understand it. Then immediately I say, oh, that is something like, if I'm not, I taught something and they didn't get anything, even the sincere students didn't get anything. So there may be some kind of change possibly should be there. Then we thought of, okay, let us create some visualization. This is a visualization which I made. So here, star means is the Poisson probabilities, is the PMF for Poisson, and this circular region means it's, or the ball means it is a binomial, right? Binomial probability mass function. So when I have n equal to 10 and p equal to 0.3, as you see that there is a much difference between these probabilities. I'm now kept my n 10 and p equal to 0.1. You see that this guy seems to coming close to each other, right? So what is the binomial probability values? One is the Poisson probability values. And similarly, for n equal to 20, p equal to 0.3, you see this is a something. P is moderately bigger here, so still we can see some kind of difference. When n is pretty large, say 30 and p 0.1, as we can see that most of the probability values are coming to each other. So as n increases, the binomial probabilities are well approximated by Poisson probability. So when I show this picture, my all efforts are done. Now what typically we do it. So we look for some books where such picture is there, we copy it and paste it in our own presentation and show it and give some kind of a demonstration. And that figure, probably till my retirement, that figure is going to be fixed, and I gave this to multiple places. But here, because of this effective dynamic documentation, we have an extraordinary way of doing it, because this figure is embedded within the document because of this particular piece of code. This is the piece of code which I have written. Here, if I make some changes, the same changes is going to be reflected there. And every time the new picture is going to be generated without there. So there is no copy paste, there is no hard works. The other ones, right? Here, like nowadays in advertisement, we see earlier when we are child, we are only taught by our parents that hard work. But now I think because of the entrepreneurship and everything, skill development, everything, now there is also something called smart work. So I think some advertisement also is there. There are two families, one father and one son. and there are two pictures, and they are conversing, they are having discussion with their kids. And so one father is saying it is hard work, one father is saying it is smart work, and there are different comparison. I just saw couple of days in television. So it is something like this. I heavily got benefited, and students also got benefited. And because of the reproducibility, it is something very important that whatever we do, a figure that I have created, and I forgot that how that is being generated. It is not going to happen. In particularly in research in science, we are probably in a good situation, but a lot of things are also happening where which we call it as a reproducibility crisis. So now most of the workshops in many of the places, in fact, in the last workshops here, there was a specific session on reproducible research using softwares. So you have to ensure that whatever the codes, by making, how can you do that? By making our codes which we are writing, it is reproducible. Only initially it takes some time. After that, things are very, very efficient. I'll show one example how we are implementing this in our research activity also. So the same thing is in Python being written. So some students who are interested in Python, they can easily, this the same code will be generated. Same picture will come. For the connection between poison to normal, again we apply that MGF and everything, and we do it. So here again, I took some time and write down this R codes. Please note that first of all, nothing of this copied from anywhere. These are all are exclusively completely written by me, and I'll share also this material with you all. So there is no, it is everything is free. R is a free software, and we believe that education and research everything should be free only. So it is absolutely fine. So, however, I should explain that what are the things has been taken over here. So for example, normal and Poisson, their relationship. So as we know that as lambda increases, the Poisson probability questions related to Poisson distribution can be well computed by the normal distribution as well. So this is a visualization for that. And when you show this picture, students easily understand. So which seems to be, and I saw that this is working pretty well and pretty nicely, right? So there are similarly connection between normal and p-distribution. We had this famous problem of testing of hypothesis, where sometimes sample size is less than 3 and sample size is bigger than that. So we know that if we compute the probability based on normal table and compute the probability based on t table, there is a difference, right? But here, when we are in the field of data science and machine learning, we are equipped with a whole lot of data, big data scenario. Then many approximations works automatically. However, why that approximation works? For that, typically we go for a Stirling approximations and show that the density function of t acts like a normal density, converges here as the degrees of freedom increases, as p increases. However, graphically it only means that the, if I see this light green, this is the one which is normal. As is n equal to 3 means this is the t distribution at 3 degrees of freedom. It is thicker tail than the normal, right? N equal to 5, it is this one. As you see that as n equal to 10, it is more close to the light green color. So that means as your degrees of freedom increases, the probability distributions eventually converges to the it is normal distribution. So that means if n is large, the t distribution curve is very approximately equal to the normal distribution. So when you are comparing probabilities or computing probabilities of key values, whether you are using normal table, whether you are using a t table, the difference is extremely small. It may be 10 to the power minus 4 or something order. So that is the, so once we show this picture, our work is done. So effectively using statistics for real data analysis, it is very important to understand some of the basic ideas and fundamental ideas. So as you see that this document is still undergoing, it's still under creation. So like there are many more things will be added over there. So as you can see that this is a very effective way. Sampling distribution. We always say that if I have a x1 x2 xn as a random sample taken from, because typically we write down like this. Those who are here statistics, they know it already that we write it down x1 x2 xn. This is IID normal mu sigma square, then xn bar follows normal mu sigma square by n. And if we typically we utilize MGF technique or transformation technique or characteristic function technique, and by that we usually prove that. So we say that it is a sampling distribution of xn bar. But in principle, what I mean, so for example, if we want to explain it to some other domain people, that this is what it is. So that's it. So what I have done, I simulated numbers from the normal distribution and take the average. Again simulated random numbers from the normal distributions. Again I have simulated. Again I have done. And I plotted the histogram of the sample means. So it becomes normal mu sigma square by n. And this is the PDF of normal mu sigma square. And this is a very good match. Similarly, that this is the distribution follows a chi-square. Okay, that's wonderful. You see that the for multiple rounds of simulations when I did, we calculated this quantity and draw the chi-square n minus 1 graph on this chi-square. Similarly, for a normal distribution, we always know that sample mean and sample variance, they are uncorrelated. They are independent basically. We say they are independent. And we have a 3 pages derivation for that. But if I understand correctly, if I simulate the data and calculate sample mean and sample variance, so I get two values. This simulation procedure I continued for say 1000 many times or 100 many times. And if I make a scatter plot of between them, then I should not see any kind of pattern among them. And we know that such kind of visualization essentially represents a signature of independence. So means one is not going to be impacted by the other. Right? So many of the theories, because of this extremely powerful dynamic documentation, many of the ideas, many of the statistics, probability ideas, which were not accessible to like engineering students, to some other background people, these things are now getting very accessible to them. Because finally, we want to efficiently and effectively apply these concepts to solve the real life problems. So I should not apply them blindly. So, for example, I'll just show uh, one more example for it, and then I'll get into the next topic. For example, one of the particular idea which we all struggle with the convergence idea. When for statistician, what I have observed that when we come up with these convergence ideas and everything, we suffer a little bit more because there are a lot of mathematics concept comes up. So in mathematics, we have only one, I think only one type of convergence. When we talk about real sequences, definitely that uh, uh, that it's deterministic points and it converges to particular point. But whenever we start even convergence in statistics, we automatically ask the question: okay, is it convergence in probability? Is it convergence in distribution? What kind of? It is convergence in mean or eighth mean or third mean or second mean, a whole lot of things that comes up, right? So, however, because whenever we read those things, those are very mathematical in nature. Again, see that these are all the things we have taught in our UG and PG. So it is a kind of way we try to harness softwares or the programming as much as possible to plant those ideas into the students' minds. because they should not consider something that it is something. Rather, the students, I should also consider the same thing. That I should not feel that it is only just concrete theories which does not have anything to do with the real life applications. But no, like effectively we can communicate it, effectively we can understand it also. So for the one of the idea that people always use is kids said the weak law of large numbers. It only says that sample mean converges to the population mean. So the idea is very simple. That if I say, for example, like typical example what statisticians give, that if I take, my class has 150 students, and I am interested to know what is the mean height. So this is not a example from machine learning researcher. This is an example from a statisticians. I'll give you some machine learning example also. Like, although the idea wise they are same, but typically a statistics teacher give an example that if you have 150 students and I am interested to take the what is the mean height of the class, what is the mean height of the class, then I randomly select 10 students and I take the average. Okay, and we ourselves know that it is subject to sampling variation. Means instead of me, if somebody else would have collected the 10 values randomly, he will also get a mean value which is going to be different than me. Like this. So that means my estimate what I have got based on the 10 students randomly selected, which has a which is subject to sampling variation. So that means the distribution of the sample mean is pretty wide. Now instead of 10, we know that if we select say 50 students, it does not require any mathematics. Common sense. Intuitive says, okay, you have selected more sample, that means your average will be more accurate. Will it be exactly accurate? You would say no, it will not be exactly accurate. It is going to be more accurate than 10 for sure. If I take 100 students and take an average, you are more confident now about that, about the uh, about the actual mean value, that you get a very good estimate of that. Why is that? Because the variance associated with your or standard error associated with your approximation is very small. So if you take 100 people and 10 and you and your friends perform this experiment taking 100 values and take an average, so you are going to get many average values. The variations are going to be very small there. If you take all 150 students, you hit the exact mean. That's precisely the idea of weak law of large numbers. It says that as my sample increases, we get a better estimate of the expected value or the average value or the mean value. But now this is an example which I have seen. When I explained it in the class, student thought that this is again sir has come up with some kind of hypothetical example. But students know how to write a loop. They know how to write a matrix in a using a software. They know how to take an inverse of a software using inverse of a matrix using softwares. They know how to write a loop. They know how to store the values. These things they know. Why can't we utilize students that capability to implement this in using a software? We can then we throw that problem to the students. We say that okay, what you do, you simulate 10 numbers from Poisson distribution and take the average. And we know that for a Poisson distribution, mean is lambda, right? And algorithmically, you continue this process. Sorry, what is the algorithm? You randomly select one sample from a Poisson distribution using the software. So by now you have learnt about uh, how to simulate random numbers. So I am just putting a message over here. Okay, there some messages come. Let's come. So I am assuming that you know R norm R was etc. Okay, please put a comment here. Okay, in case you don't know, I'll just show a small demo as well. So what we are saying to the students that you take the first, you select a random sample from a Poisson distribution using the software and store it in Y1. Now you randomly select two sample and store it in Y2. Like this you continue. You randomly select n values from a Poisson and then take their average, store it in Yn. Now plot this Y1, Y2, Yn values. Let's see what is happening. This is the R code. This is one of the demonstration. What is that? What we do that? The same process we do. First we do for n equal to 2. So that means there are several, we have taken a random sample of size 2 and I told this to be done to 100 students. So this is the distribution that we are looking at. Then I take n equal to 15. So I instructed 100 many students to randomly select 15 values and calculate the average and give me those values. I draw a histogram. It got heavily concentrated. As the experiment is done by for 500 sample, you see that the variations of the average that they have got, it becomes extremely small. So that means as sample size increases, the sampling distribution is getting highly concentrated at the population mean. Right? Now you understand that. Now what is the main focus I want to put here? That this is the graph which you are looking at now. Please understand this part is most important. This graph you are looking at now, you probably liking it. It's very nice graph. Okay. However, if tomorrow, if next lecture, if I want to demonstrate this using some other distribution, not Poisson, I can do it immediately because because the idea is here that so I have written another file for this that converts these concepts. This is another markdown file, right? This is another markdown file, and wherever the code is particular code is there, where I'm simulating Poisson distribution, and I'm just going to utilize that using the other distributions which you want. That's it. The change that I have made for a some slight change that I have made is going to be that only. No other extra effort. Automatically, all the pictures are going to change. There is no work that you are going to do for manually to do all these things. Similarly, those ideas can be very well approximated, very understandable for different distributions. You can do these experiments. You see that as sample size increases, your sample means getting highly concentrated in something. Right? So, for example, this is also a wonderful visualization. Actually, the experiment that which is discussed is automatically, eventually, these guys are getting heavily concentrated towards the expected value. So, this dotted line you can see it is nothing but the expectation. Let me check out the any comments or not. Okay, there is no comments till now. So, please drop a message also. No problem at all. Okay, so this is another thing is that way of dynamic documentation, some examples also being put over here, right? So this is something you can just play with it. You can just play with it. You can utilize it for demonstration. You can utilize it for many purposes. So this is the R markdown documentation, which is extremely dynamic in nature, and you can make out many other documentation as well. For example, presentation. So you can also make a presentation using R Studio that looks super, and then you can create quarter document. This is a very recent newly addition. So this is also a very like if you have a those who have used Python, you have the Python markdown. So quarter documentation has a wonderful feature. It gives you a like that wonderful documentation in the web. That feature it gives. Shiny web applications. I'll probably show you some kind of shiny web application as well. And then definitely you can separately Python script. Those who are using Bayesian user, many people use Bayesian methods in their research and other things. In particularly Hamiltonian Monte Carlo methods, those type of methods are extremely powerful in Stan actually. So this is another softwares. Its installation is an issue, but R provides a very wonderful platform where you can write down your stan files as well for doing Bayesian computations. So you can create an HTML file also. They also then you have an R documentation file also. So there are many options. R notebook also a very wonderful feature. Plumber API I did never used it. So but many of them I have used and I utilize also for the purpose of teaching and research purpose. Any question? Is this fine?
Yes, sir, it's fine.
Okay, okay, thank you. So this is the document. The first one was the introduction to probability distribution that I'm going to share with you, and definitely you try to generate your own code as well and own documents, and if there is an issue that you face, definitely I can be contacted. I can discuss it in the upcoming sessions. Okay. So this is a demonstration for the yes. So this is a demonstration for the dynamic documentation using R. Now, one thing, as I saw that there are, because we have one session on differential equation solving using R as well. So another section will be there. This material also immediately after this session it is going to be shared with you all. So let's now try to give a very brief. So this is going to be an application oriented, that how we apply the things in our research, in our research works. So for example, one of the applications, I'll take two different applications. So whenever we are having, say for example, rather than biological, I'm just writing, say only writing as a say growth curve models, right? So basically it is used for many purposes. It's basically turns out to be a differential equation, and you're looking at evolution of some state or evolution of state as a function of time. So evolution as a function of time t. So typical example in mathematical biology community, because as I understood, there are two communities in this, like largely dominating community in this audience. One is mathematical biology and one is statistics. So this is the problems which will serve both the audience. So for example, if you have a dx dt, so that means it is a rate of change in the population or the state with respect to time, and this is usually right. If this is the case, I think we call it an autonomous system. So this is a differential equation. So if you give some initial condition over here, then you are going to get the evolution of the population or evolution of the state over time. And now you have all those uniqueness and existence results from the differential equation techniques. We are not going into that. Those are, but our concentration is that I am having such a differential equation. There are two aspects, that how we can solve such a differential equation using the software R. That is our first task. And second one is that how we can calibrate or we can fit these differential equation models using the data. This is from the statistics part. Another part also is that now we have this differential equation and we have this data. So this is the observations that we have collected at different time points. So this is my data. How we can calibrate these differential equations, or we can estimate the parameters in these differential equations using this data. Now, typically, when you are working in a mathematical biology domain, we rarely end up with one single equation. For example, when you talk about this disease propagation, or like during COVID, lot of mathematical models have come. So you try to capture different biological information or different information about the disease and pathogens are available. You want to incorporate their behavior into the mathematical model, so it becomes pretty complex. So you usually end up with, say, dx1 dt, or let me write down only x dt something, dy dt something, and dz dt something. So you usually end up with system of differential equation. Right? And you want to calibrate, or rather than calibration, I must say, you want to estimate the models, and there are a lot of parameters involved here, and you have got the data of disease incidences over time, or number of hospitalized cases, or number of quarantine cases. So there are several data from either from government portal or either from hospital that you get, and based on those data, and you have a hypothesized model. So if I write it down, so based on the biological information, you create a mathematical model. So this is the math world. Then from the real life, you got a data over here. So you got a data, and this model, it is heavily parameterized. Usually it is heavily parameterized. So now you want to use this data to estimate these parameters, and based on that you get a prediction model. You can call it as a aim hat, right? And based on this, so prediction model, and this is, you got an aim hat, another model. Based on that you take decisions. But there can be other scenario also. So this is, you prepare, or you only one model, and everything, every prediction, every decision making is based on this model. But however, when somebody asks the question that, okay, so how did you know that you have captured all sorts of things? How did you know that there is no other alternative possibilities? So that means it might also happen that that you have this reality, and from this reality you have got this data. Now as an investigator, you thought that, okay, so should I come with a single model? I almost did a very powerful literature survey, come up with a very wonderful model, and I saw that it is giving a decent fitting with the data as well. So summary statistics is supporting my my model nicely. However, that still there seems to be risk is there, right? Risk will always be there, but you want to minimize that risk probably with some additional efforts. Okay, so rather than, you thought that since I don't know how God has played the game or nature has played the game, let me consider some multiple possibilities of models. So you thought that, okay, this can be a model. Okay, okay, so this data possibly can be modeled by using this model. Okay, so let me consider that there can be some other model as well. So that means what you do now, you are going to calibrate this model, and you are going to get m hat. So another, based on that you could take a decision. You could get a m2 hat. Based on that you can make a decision. Based on that you can have another model. There also you can take a decision. Or you can combine all of this model and take another decision m hat, which is a ensemble of models m1, m2, and m3, right? So that is going to give you a kind of a ensemble predictions. So you are not able to say that 100% that m1 is the correct, most right model. With 100% you cannot say that m2 is the right model. So there is certain level of confidence associated with which model turns out to be the, which model is the correct one. So based on that, and we have different models, and you fit it all those models based on the data, and then you can take different decisions, or you can ensemble these models and make a predictions for the future based on this data. Again, I am assuming, so if it is not, and logistic regression and random forest. So you already have actually got an idea of this ensemble thing, because random forest here basically you create a very large number of trees, and based on this that trees you take the decision, right? You compute your probabilities, right? So this is something that ensemble learning, in particularly in machine learning literature, that ensemble learning is extremely powerful, because typically when we have studied in our classroom, or when doing some problem only for getting marks, there we always come with an assumption, because in the question it is given, you are given some data, and assume that the underlying population is linear, it is fitting a linear regression line. Say underlying population district relationship is a quadratic, so estimate the parameters a, b, and c, right? Or the underlying population is an exponential, so you estimate those parameters for the rate and the initial size. So that means always you have an assumption about the population model. However, in general, when you are dealing with real life case studies, and you are actually solving a problem, in that case you will going to have only the data in your hand, and probably some information about the system from which the data has been collected. So you can understand that you have the data, and you have some partial knowledge about the system under investigation, right? So based on that, it is extremely difficult to work with quote unquote some assumed model, because when you are assuming some model, it means that you are assuming that how nature is playing the game. So rather than you are saying that okay, I'm just want to be more vigilant and minimize my risk of having a very wrong prediction, so if we take an ensemble of different models, then it's likely that I'm going to have a reduced uncertainty in my prediction exercises, right? So that idea is very simple. Ensemble means if you take multiple possibilities, then you take an average, you are going to have a reduction in the variance. That's the fundamental idea. This also I'm going to discuss, and this case also I'm going to discuss. And please understand this, that along with how we do it, the codes and everything also be available to you. Okay, so it is not that just we explained and it is gone. No, a separate material will also be given to you, where example and case studies will be given. Example case study will be given, and how you can apply it for uh, your problem if it is matching with there. So let me take out the first one, first problem. So let me I'll talk about it, but before that, let me take up this issue since I have already explained it, that you have a model which is a differential equations, and you want to solve it using R, and also you want to fit this differential equation using the softwares. Okay, let me try out. Again, as you see that the power of dynamic documentation. So I've written a document for you, that introduction to growth models using R. Okay. Again, it goes for fundamentals of mathematical biology. So this is the heading that I had given over here. Again, let me execute this and check out that what it is coming. I have got something, but I think till now I have shown you only building a PDF. So let us just take this an approach. Let me just show it you in a user what is called as a like HTML itself. Let's see what is it coming up. So please understand this powerful thing. Everything what is happening, it is happening dynamically. So there is no static file that I updated before your lecture. I just updated this R file. Okay. So this is what is has appeared. So I can open it in the browser also, like the way which is the sample that I have shown. So this, look at this. This is the document which is come in there, right? So then I have put some description over here. So then you have some common growth equations. I have given a description over here, right? So this is the differential equations which we say that the so dx dt means it is the change in the population size, or absolute change in the population size, but when we divide it with x, it becomes a relative change in the population size, and the relative change in the population size is governed by birth event and death event, right? So if I have the birth rate is d b and death rate is d, so we can model under this assumption, we can have this differential equation. So if I just reparameterized it, b minus d equal to r, right? And you start with some initial condition that x0, then you get x0 is equal to, this is the solution which you got. Everybody knows it is going to have an exponential distribution. That population is going to explode exponentially as t tends to infinity if r is positive. So means birth rate is more than the death rate. If the death rate is more than the birth rate, then it is going to have an exponential decay. If r is equal to 0, that means birth and death they are equal. In that case, population size does not change. Let me have a look at the syntax first. Okay. Again, you see that this is no, don't have a separate file. This is the single file. This is a description. This is the common growth equations. So this is the what is the code that I'm writing over here, right? So state c is equal to c x comma x equal to 10. So that means I have started with initial population size 10. Now you see that what is the benefit of having within this file, the code within this file. The benefit is like this. You can see this is the symbol run current chunk. Means you don't want to execute the whole document. You want to execute only this much piece of code. So you just run current chunk. You see that? Ah, only the current chunk got executed. So the whole document did not get executed. So what I have done, I assume the initial condition, say that there is a comment also at x equal to 10. Parameter I have considered r value is 0.3, which is the parameter value. Then we require the package d solve is the package, main package for solving differential equation in R. Then I have taken a time points at which I want to draw the want to find out the solution. Then I have to define the differential equations. So this is the exp function, exponential function. This is my function. It takes three inputs. One is t, at where you want to solve. State means what is the state variable? Here is x. And param, what is the parameter value that you want? Now inside this function, this is a common syntax for all. So with as dot list c state param, and this is a differential equation, dx is equal to rx. So this is the description they wanted, and you return the list cdx. So you return the list of the increments. So this is the what is the r would require. Then you take, then you run the function ODE, which is available in the dsolve package. So what you can do, you can write down library dsolve, and you can write down help ODE. Automatically has come, right? You can get some help from the ODE, and you can see that I think mathematical biologists are mostly comfortable with this RK4 method and ODE45. And you see that this contains all of these methods, right? Adams method, right? There are many possibilities are there, and Euler method, that is the Taylor series method with the first order, keeping the first order. So there are multiple things are available. There are methodological descriptions also there, so you can easily get that. So OD 1D for 1D models, OD 2D for 2D models, or 3D models, right? You can basically play with it, right? Now this is the function. OD is the function which is you have to pass the times. This what is the in which time points you want the solution. You have to pass the state, means the initial value, and you have to pass the function for the differential equation, and you have to params is equal to parameters. That is what you need to, parameters the values of the parameters which I have stored here. So that you need to, pass, right? So let me execute this, right? Then head dot out means, so let me check out what is there in the out. So this is the out values that has come. So head dot out means that you start with initial 10, and then rest of the values are getting calculated. That it is performing that numerical integration of the function and computing that, right? Then you may want to plot it. This is your, so this is the curve when you have a R is a PGR profile, means per capita growth rate profile, means 1 by x dx dt, and this is your absolute growth rate profile. So that means how population changes. So dx dt is equal to rx here, and this one you want to plot the times, means what is the output from the at which you have calculated the value. Out contains the output of the solver, and by putting this x means you want that particular column. So if you see the head of out, right, you see this x. So if you write down out, right, there's a two columns, and you write down x, you got the first column. You have learned it, or you give it two also, you got the second column, right? So you can read out this by using the, okay, this small x capital X. As you see that it is capital X. Head of out, you see the name is capital X. So if you want to access that column, you can either provide an indices of that column, or you can provide the exact name of that column, right? So this, if you do this plotting, this is the solution that is being provided to you by the program itself, by R itself, right? Now, as you see that this is the solution, this is how differential is being solved in R. And since we have executed only this part, run current check chunk. Since I don't want to execute the whole document, only this much. So at the end of chunk, you will be getting the outputs. So you see that it is shown the output here, right? This is the output that you are going to get. You can minimize this output also, and you can see the output. I'll just show it to you. So let me execute once again. Right. So this is the plot, and you see that this is the one comment was there for printing. This is the plot. Here I have plotted all the things together. PG or per capita growth rate means 1 by x dx dt. Absolute growth rate means only dx dt. And size profile means this is after solving the differential equation. Means this is x0 into e to the power rt. So now see that there are other code chunks also, but after this code chunk there is no such thing. So if I execute only this part, there is no picture over here, but here only within the document you can able to visualize this picture. So wonderful, right? You continue writing your document. That's it. Like forget about those ideas. That I'm writing a code over here. Then I'm parallelly writing a LaTeX file over here, or parallelly writing a Word file over here. I'm generating the things here and getting copied and pasted over here. Then there is a nightmare to managing the size of that picture and everything. So forget about it. You start writing your document. You want to make some teaching material or some research material. You just start writing your document. Okay, this is what I do. And in between, you just infuse your codes wherever it is needed. Just include the codes. Based on the code, automatically the figures will be generated. And most importantly, you can manage the figure heights, figure width. There are n number of options are available. So figure height, align, right? Figure dimension, figure height, whether you keep the figure, many things. You can include extra figures, fig width you can control. There are a lot of options are there. You don't want to run that piece of code inside it, that is also absolutely fine. So it is extremely powerful tool. I hope you are able to you are taking the, because I myself have found it very useful when I started using it. So I just started writing the documents and I just embed the code inside. The same thing I do in my regular lectures also, and eventually very wonderful documents are being created, right? So let me just show you that how this document looks like, and we will take it, right? I think this is the document. Earlier it was a very small document, now it has become pretty big document. There are many other Python codes, everything will be embedded. So I'm also planning to create a series of basic documentation for fundamentals of mathematical biology, and in particular how mathematical biology is getting integrated with data science and machine learning. Because in general, lot of research in mathematical biology is happening which are concentrated on the dynamical systems and their stability analysis and understanding their bifurcations behavior, and many things seems to be very mathematical in nature, whereas unless we calibrate or we estimate those models in the light of the data and performing multiple comparisons, it is difficult to make it useful for the uh, for the for the real life case studies. So this is the fitting of these equations. Then I'll also talk about uncertainty quantification. So see that this is the document which is getting created, right? With various examples. And definitely I'm also going to talk about, I'll brief through it this document, which will be shared with you. And I'm also going to talk about immediately after that, talk about when we are dealing with the multi-dimensional scenarios. This is the case study which I'm going to show it to you. And again, there will be a document for that which we have created for you all, so that you can utilize those things. Yes. Now let me just brush through on this document, and which will be shared with you. So when we were talking about the population dynamics, and then definitely this is one of the very important model that comes into play, which we say it is a logistic growth model. So please, the solution turns out to be something which don't mix it with the logistic regression model that what you have seen in the machine learning. So this is a logistic growth equation, this is a differential equation. So its solution is going to have the similar shape of the logistic function what you have learned in machine learning, but the contextually here things are different. So that we need to get that clear. So again, I do the same thing. So what are the things we need if we want to solve this differential equation using R? We need the differential equation description as a function. So what I call is a logistic function. This is the name that I have given. So this is the differential equation. So this is dx is equal to r into x into 1 minus x by k. Because if I take this x over here, this is what we get. And what is going to return? It's going to return the list of the differences dx. And state means initial population size you have to give. And parameters means you have to give two parameters here, r and k. And then you have to provide the times. And then you are getting a ODE of this function, right? And you are printing the 6 rows. So you just don't have to do anything. If you just copy this whole thing and open up a new R script, paste it over here, and execute this. First line got executed. This is the solution you got, right? And we just plot the solution. Let's make a plot out of it. This is going to be the plot of this. That's it. So the document is there with you. You know how to do this. So you can now you can play with it. Say if you give r is equal to 1, what will happen? It is going more faster towards the carrying capacity k. So if you give say 0.1, the carry, so it's getting, so the growth rate is low, so that it is getting, it is approaching to the carrying capacity later. So you can say, for example, you can increase the time by say 50. Again, you can do the solution. See that now it is going very late. So if you give 0.2, it is converging to the carrying capacity K. So how do you put this carrying capacity K here? So you are right. AB line, you note a horizontal line at 50. You can give color equal to red, LW equal to 2, and line type equal to maybe 2. So this is the red, or instead of red you can give blue. So the trajectories are basically eventually converges to the blue type, right? This is something. So you can play with it. Now you can give different initial conditions. So you can say 80. So in the top also it is eventually it is going to go to the. So those are coming from mathematical biology background. They know that here the population, the k parameter, the parameter k is actually called as a carrying capacity, and it is the stable equilibrium. What it says that as time passes, the population is eventually going to settle down at the carrying capacity k. So this the physical motivation people express in that way, that we have we are limited with finite resources in a place, right? And the populations keep on growing. Eventually, they will have to settle down at some cap, so they cannot go beyond that. So that is the cap. What the finite set of population the current environment can hold, it is typically referred as a what is called as a carrying capacity. So here K is the carrying capacity. So just to for the who are not from a mathematics this particular background. So this is the equation which we have. So Rx 1 minus x by k, and if we put is equal to 0, that is going to give you where there is no growth. So dx dt is equal to 0 means no growth condition, right? So there is no change in the population size happening at which point. So this gives you two roots. X star is equal to 0 and x star is equal to k. Now there is some technology which we call it as a stability analysis, that whether the population is going to settle down at 0 or whether the population is going to settle down at k. This is to be determined. So here, as we can see that you start with any population size, it is going to population size eventually going to settle down at the parameter k. So k is called as a stable equilibrium. Right, so you can create some nice visualization out of this. So for example, this is the solution which is given to you. In the following code, the absolute growth rate, relative growth rate profile, so we can draw their absolute growth rate and relative growth rate also. This is the per capita growth rate, and this turns out the absolute growth rate. So these are the common pictures what mathematical biologists draw, that this blue color or the green color means this is a stable equilibrium. So population is going to settle down over here, and this is basically it's called as unstable equilibrium rate. So population is going to, if we start very close to 0, then population size will be shifting away from the point 0. I put some description also. So even if you do not have some mathematical biology background, you should be able to read it. Now we are trying to understand, visualize this particular thing, that is that the population is really getting settling down at the carrying capacity. So for that we take various initial population size, and this is the logistic function. And for each of the initial population size, I am going to simulate this and plot it in a single plot. So this is where we have plot in a single plot. As you see that they all are eventually, from wherever you start, they all are eventually going to settle down at the carrying capacity K. So this is another equation. So a little bit of description is given over here, so that, so what we are learning, that how we can solve differential equations using the software R. So I think we understood it quite well, that this is the general format of the code, that you have to write down the differential function which will take as an input as the dx, that basically the increments, and you have to solve it according to that. Then the function OD is there with which we can solve this particular equations. So similarly, there are other examples also I have put here. So there are certain references which are ours as well. So we have also, right. So this is, I have tried to put down some of the interesting characteristic about Gompards, that where the population is going to settle down. For a Gompards equation, population gets settled down at some point, but it depends on the initial population size. If your initial population size is more, it is going to be settled down at higher. So from where initial population you are starting, accordingly, so the quote unquote the carrying capacity or the fixed point for the Gomparch population model, it is a function of the initial population size. It's not just a constant. Similarly, another one is a very popular equation in the field of mathematical biology, which is called as a theta logistic equation or generalized logistic equation. So I gave some references also, which they put here to the power theta. So theta basically it is sometimes also called as they put in asymmetry or the measure of asymmetry in the population size. So what kind of asymmetry it gives? This again, there is a solution for different values of theta. So theta we have for this is a solution which is given for different values of theta. Again, this particular code is available to you. You can execute and choose different values of theta, and you can see that how the population is getting settled down. Here also the carrying capacity K is a fixed point, and it is actually a stable point also. So this is the rate of per capita growth rate or per capita growth rate profile for different values of theta. So if some, well, if probably if you're lost somewhere, I just want to push you to understand little bit of the things that if we plot over time over x dx dt, right, then we call it as a absolute growth profile, AGR. For example, here dx dt looks like for logistic rx 1 minus x by k. So that means it has one root at 0, another root at k. So this looks like this. And maximum is attained at k by 2. What is PGR, per capita growth profile? It is x here, and here you have 1 by x dx dt. So if we do this plot, 1 by x we take over here, then it becomes r into 1 minus x by k. So this is the point 0 comma r, and this is the point a comma 0. And another is size profile, which we call it the size. That along this we have t, along this we have x. So that means something like this. So this is called as a absolute growth rate profile. This is called as a per capita growth rate profile. This is called as a size profile, right? And in the same fashion, when we are considering that dx dt is equal to rx 1 minus x by k whole raised to theta, do you see that there is asymmetry is happening? How is that? That x, this is dx dt. So depending on theta, this is 0 comma 0, this is k comma 0. So depending on theta, this shape can be like this. This is when theta is equal to 1, right? Where the maximum is going to be here. So here can also maximum. So there are multiple possible maximum. So that means at what, answer the questions, that at what population size they have maximum rate of, yes or no? So what is the maximum rate of growth? So when theta is equal to 1 symmetric, then x star maximum growth rate is equal to k by 2. However, when there is asymmetry over here, then the maximum are shifting, and these are shifting as a function of theta. So this is a very important observation, and several research articles that has attributed. So this is very statistically very interesting, and a whole lot of it, including research articles in Science, including Nature, and the statistical estimation of this parameter theta, estimation of r and theta. Several research articles. So it is a very vibrant research area as well, that understand the population behavioral growth, because they have they have associated these parameters r and theta with the life history of the population itself, because they are indicator of some of the evolutionary characteristics of the population itself. So these estimates are very important, and there are several, not only one or two. Lot of efforts by statisticians have been made in getting accurate estimation and interpretation about the parameter theta. So, as you see, the articles are appearing in Science, Nature, and several top journals. So, this is really a very vibrant research area, which will challenge you in both the sides. It will challenge you from a mathematical biology side. It will also going to challenge you from a statistical point of view. So these are the plots. As you see, there is an asymmetric plot is possible here for different values of theta. So as a research domain, I put, since I work in this domain for a long time, so I put some kind of notes also over here. and some references which may be useful for you. Now, this is another particularly important growth equation. It is something like this, that suppose that you imagine that you are working with a population which is growing in an environment that they need to maintain some minimum population size so that there is a possibility of mating and reproducing for the next generation. So if a population size is low and they're in a sparse scenario, so in that case they may not be able to survive. So that means there is a minimum population size that needs to be maintained so that they are able to grow. So it is something like this. So that means if I understand from a very, very intuitive point of view, that means this is the growth of the population. Okay. So if I consider it something like this, that Rx 1 minus x by k. So this gives me an equation of this form. So 0 comma 0. Along this I have x, along this I have dx dt. I thought of taking it as a very, very simplistic way. Okay, so this is k comma 0. So as you see that throughout the growth rate is positive. So population is uh, going to increase and going to settle down at the k point. However, we are saying that there is a threshold. This is 0 comma 0 and this is x and this is k comma 0, and there is a threshold population below which when there is going to be an possibility of extinction. That means if dx dt is equal to 0 or this is less than 0, then when there is there is a uh, uh, negative change in the population size, that means we are prone to extinction. So that means it will happen. How can this can happen? So suppose that this is something x naught, and after that it is negative. Above this it is positive, below this it is negative. So that means I have got two bends over here, right? So this maybe I let me use the same notation what I used over here. So let me call this A. So that means I got a cubic equation for this now. So this equation can be represented as Rx x by A minus 1 and 1 minus x by k. As you see that when x is less than A, this guy will become negative. Rest everything is positive. So and A lies between 0 less than A less than k. So if x is less than A, this guy is positive, everything is positive, but this guy is negative. So dx dt when x is less than 0. So that means this is a growth profile or is a growth curve which says that as my population size gets below the level critical level A, and sometimes people refer it as a LE threshold. And definitely for mathematical biology, this is one of the very, very important phenomena, and whole lot of research on LE threshold. I think its estimation and also looking at it from a various nonlinear dynamical systems analysis point of view. Lot of research articles have come up. And good news for statisticians also, because estimation of LE threshold is actually very challenging for real population size, and this is one of the very important part of population viability assessment or the conservation management plans. So these models are being very wonderfully used in those cases. Okay, so that's an estimation part. So let us try to see. So that means what should happen? That if we start from an initial condition from x naught, from here, the population should settle down over here. If we start from population size x0, then it is going to go extinction to 0. So that means here A is an unstable point. And whereas A is basically separating to this is actually a stable point, and this is another actually stable point, right? So that means A is an unstable which is separating basically two stable equilibria. So this is a typical case what we known as a bistability. So please understand that for a statistics point of view, how we actually visualize this. This is a deterministic system. It's a differential equation, and this has three equilibria: 0, A, and K. So X star is equal to 0, A, and K. So how do we visualize from a statistical point of view these scenarios? So that means we are going to have, so when we analyze this system in a stochastic environment, we are going to have two modes, right? One mode is going to be close to K and one mode is going to be close to 0. And and the distribution would be almost close to 0 over here. So it's going to have a bimodal probability distribution. Analyze the system in a random environment. Okay, so let us just check out that how this thing looks like. So as you see, whatever we thought, this is expected to happen. Our very simplistic thought that there should be negative below which, so we just end up with the cubic equation, nothing else. This is precisely what is happening, right? If we do the solution of this, and this is precisely that if you start above A, then it is going to be settled down at K, and if you start below A, the population is going to extinct. Very, 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 very important concept. And this identification of threshold, or if you are giving me real data, and whether such a threshold exists or not, that's a very, very important and challenging problem for both statisticians and mathematical biologists. So again, this is a PGR profile, and this is the profile which I have just shown you on the picture by a drawing. So as you see that the purpose of this documentation, again I go back to this document every time I'm emphasizing on this, that when you are writing these things, and if you want to make some modification into this document, you don't have to create once again. So the same document, wherever is needed, you just make necessary changes, and again you build this document and you get the results that what you are getting, right? So these codes may be useful to the mathematical biology aspirants also, uh, who can utilize these codes and do the analysis, the generation uh, of the problem analysis of their own. Okay, let me check out if there is any queries. Okay, so there is no queries as of now. Okay, now this part is okay. We understood it. That we understood that how we can solve a differential equation using R. Now the question comes that because we are going to have a real data, right? So let us try to understand, right? Now suppose that we are a population, say for example R is equal to 1, right? And you take T is equal to, say, sequence of from 0 to 5, so y is equal to 0.1. So you all know about this. Okay, if you print T, then I'm getting these are the values. Okay? So what will be your X values, the corresponding the solutions? And if you suppose that you start from X0 point, the initial population size, say X0 start from say 3, X is equal to X0 star exponential of R into T. Right? So if you plot T comma X, type is equal to L and call is equal to red. You can give some red color. This is the plot. You can put line width equal to 2 also. This is basically the exponential growth you are looking at. Okay. Now, suppose that now you have collected some data. You don't look at this data like this, right? Because you want to get this uh, fitting of this curve with the real data. Now, let us suppose that we artificially simulate some data. This part is extremely important, that why it is important to know that how we can simulate the data, in particularly from statistical point of view. Because when we try to compare, so for example, as very simple, one of the idea that which has intrigued me most, that when we say that I have a statistical model or method and I have a mathematical method, what is the difference that I have understood myself in this way? So, for example, we have a Newton-Raphson method or say bisection method, and I have developed an algorithm for Newton-Raphson. I wrote this, and whether this is giving the right result or not, how to check it? You consider a you consider an equation for which you know this is the root. This x square equal to 4, and you know that 2 is the root of this, 2n minus 2. You use such an equation and you perform the Newton-Raphson iteration, and you see that this is going closer to the exact root, right? So there is a validation, right? What the methods that you have written or you have developed, by that you can check it, because there are many equations whose roots are equal, for which you can check it. Now, when you develop some statistical methods, sometimes people say that okay, apply it to real data and check whether it is working or not. When I first time heard it, I felt that oh, it's very interesting. That I am developing a method and I am actually applying it to real data and working better or not. So let's try to spend 2 minutes on this. Say I have developed a new, like suppose that we have a Newton-Raphson method. This algorithm, right? You have this algorithm and you have some known equations, known roots, right? And check. So this is a direct validation possible, right? Wonderful. Now this is a mathematical method. Now you developed a statistical method. Okay? And you said that apply it to real data and see it is working better or not. Say I'm collecting real data. Say I got real data x1, x2 and xn. And I'm trying to, based on this real data, I'm trying to estimate some characteristic, some parameter, say beta, using this statistical method. Immediately my question is that what is the validation? I develop a statistical methods to estimate or approximate. Mathematicians prefer approximate, statisticians prefer estimate. So I want to estimate or approximate the parameter beta, and I got an approximation. Say let us call it beta cap. Now I'm never able to understand that whether this beta cap is equal to beta or not. Now, anybody, any scientist, or is it ever possible to know what is the exact value of beta for the real data? So, for example, from market research, I collected some data, and I want to estimate what is the probability that somebody, what is the exact probability that individual is going to buy that product, or say something. I am taking a credit card agency and uh, and I want to estimate the accurately estimate the what is the probability of this particular type of transactions are going to be fraud, or how likely a person is going to take the credit card. So there is actually a probability, and I want to estimate it using some statistical methods. However, when we collect the real data, we actually trying to estimate beta. We don't know it. So the true beta or the actual beta is played by nature, right? That I don't know. So that means we can never ever validate of our proposed statistical methods on the real data. We can apply it definitely, but before that, whether the method is working or not, for that it needs to be understood based on a simulated environment. What is simulated environment? Where you know what is the population. That you know means simulated environment means you assume the population distribution, right? And simulation and simulate from the population. So based on the simulation, you get the data that x1, x2, xn. Now apply your method and you estimate that beta cap. Now this population already having a beta and you have assumed it. So this you know. Now you know it. So you check out that whether this beta cap is getting close to this beta or not in some sense. It may be absolute sense, it may be in squared sense, right? So that is why whenever we develop some statistical methods, it has to be first tested based on a simulation where you know your population, where you know the population parameters, right? In real data, you never ever know the actual population parameters. So after the estimation, you get an estimate only. You do not get any comparison that whether this is equal to the exact parameter value or not. I hope I am able to explain this because this is something which has, uh, a, which is the uh, very foundational understanding that we have tried to understand. In another thing is that in particularly current affairs in the machine learning domain in such a way it is growing, it is that everything methods we try to apply with the real data, and this is the sense that when you are applying a method there is always a risk comes with those methods. That it's not that this method is going to be 100% foolproof, that this method is going to give you the best results. We really do not know. We really do not know. So every it might happen that so there is no method which uniformly outperforms all training data, right? There is no method which uniformly outperforms all other methods for all training data sets. It's not possible. There is no such theorem. There is no such universal theorem here. It is that it is driven by data. Every data is challenging. Every data has its own features. Every data has its own characteristics, and different group of methods may come up with the different kind of conclusion on the uh, on the same data set itself. So that's why this makes it very challenging. So what I was trying to do that first let us just simulate some data artificially. So how we can possibly simulate it? Let me start it from 10. So this is the one which we have done. Let me simulate it till say 0, 3 only. Okay. So this is an exponential growth that we know. Now, how do we, because these letters, if you're using R, some of the letters are very important. One is R, D, P, Q. So R norm is the function, say n is equal to 100. So this is going to give you 100 many values on the normal distribution, standard norm. If you draw a histogram of Z, if you put probability is equal to true, this will give you the histogram so that the areas under these boxes is equal to 1. So you know the column frequency diagram and relative frequency diagram. It is that idea. Probability equal to true means. And if you add a curve B norm x add equal to true and call is equal to Z and line with data. So more data points I take, so more accurate the histogram is going to be approximating the probability density function from which you have simulated. So just for the statistics audience, please note that histogram is also an estimator. So this is an histogram estimator of the density function f. So this has certain properties. There is a risk associated with the histogram also. Histogram is not just a boxes. This is an estimator. So there is a variance associated. There is a optimal bin width. There are many concepts comes up. So this is basically it's a curve which falls under the curve estimation problem. Now let us what we are doing. Now we understood how to simulate this. Now what we want to do in this exponential curve, we want to make we want to simulate some population artificially whose mean profile looks like this. So how can I do that? So we can do it like this. Say x is equal to r norm, right? N is equal to how many values we want. How many values we want? Say I'm writing it to be mu, suppose. Plot x comma mu. This is the and how many values? So there are t. How many t is there? We have to use that many. So length of t, right? And mean is what is the mean we want? This is the mean we want, and we can give some SD also standard deviation. So I'm giving 2 standard deviation. Let us see what is it getting. What we are getting. Let me do this task. So now we plot p comma x and if h equal to 19, call is equal to red. So this is basically the right, and try to understand that whether what is the mean profile. So if you increase its variation little bit, say now 3, see that this guy is getting more distorted, right? If you need SD is equal to 4, these guys are getting more distorted. But what is the mean profile? Interval this means this. So plot or lines p comma mu call is equal to say blue equal to 2 and LTY equal to 2. So this is basically the blue curve is the mean profile and this is a deviation, little bit deviation. So in general, you don't see this blue line, you only get the data, right? So you don't get this blue line. So you have got some data which you have artificially simulated anyway. So if I give some say starting from 20 and if I give is this equal to 5, so this is the population growth or population that over time you have recorded. Now you want to fit an exponential model to it. So there are two things you can consider: x0 to be estimated and r to be estimated. There is a wonderful function called NLS, non-linear least square, that x, right? There's the formula you have to give. What is the formula? Formula is x, right? x0 exp of r star t. This is the formula you want to have. And then, okay, so I actually forgot. What is the next thing to be given? So what we can do immediately? Help NLS. There's a formula, you have to give the data. Okay, there is a start we have to give because it is going to perform an optimization and find out what is the best choice of these two parameters x0 and r. There is a possibility to give algorithm also. There are various types of control is also there. Okay, there are upper limit and lower limit for the parameter also can be given. So it contains a whole lot of options, right? Yes, it contains a whole lot of options. So what I can just do, I can give a some starting point. Let's see how can I give the starting point. Let me see how they have given the starting point. Right? You can start this. You can give the starting point as a list. So you need to understand that you have to give in terms of a list, right? There are two starting points. Say x0 equal to I am giving say 4 and r is equal to I am giving 0.5. Right? So let me execute. Okay, it got executed. So there is a nice function called summary. You probably must have already utilized it many times. So you get the summary of these functions. What you have seen in multiple linear regression that you get is such kind of picture. Here also it is the same. So here also this is the formula you have got. This is the estimate of x0. This is estimate of r. This is the standard error of r, right? And this is the corresponding standardized test statistic value for x0. And this p value that you have already learned that if this is many star, 3 star, that means this parameter x0 is highly significant. So it is non-zero. Similarly, this one, right? And we have a residual standard error, right? This is the summary that you have got. And this you know that from statistics point of view that this is x0, we call it as a x0 hat, right? So if I can take this that x0 hat is equal to coefficients of fit. So when we write down coefficients of fit, I get two values. So that means I have to take the first entry. So 1. And r underscore hat, this is equal to coefficients of fit. I have to take the second entry, right? Now, if you can print x0 underscore hat, you get the x0, and print r underscore hat, you get the second value, right? Now, what you can do, this graph, that how good these estimates are, you can immediately plot a function of it, right? So you can add a curve. So what you can do, that you can add a one lines with p x0 underscore hat star exp of r underscore hat star p. You can add this one because this is your expected, this is your fitted line, right? You can give some color is equal to say magenta and lw equal to 2 and ldy. I think it's fine. This is your fitted line, which is the magenta line is the fitted line. So this is the non-linear least squares. Okay, the idea is very simple. The idea is very simple. What has been done over here, that you have this observations ti and xi, and I is equal to 1 to n, right? This is the observations that you have got, and you want to fit a model of this form: x is equal to x0 e to the power rt. This is the mean and plus error. So this is the regression model that you are having. So in terms of regression model, if you have x0 e to the power rti plus epsilon I. Epsilon i's are iid normal 0 comma sigma square. So this is actually a non-linear regression part. So how do you when you take the sum of squares in multiple linear regression, you have already done that. So how what will be that? It is going to be xi minus x0 e raised to rti whole square, and I is equal to 120, right? And you minimize this, with respect to x0 and t summation I is equal to 1 to n xi minus x0 e raised to rti whole square. So this is precisely what you perform, and after minimizing this you got x0 cap, and I'm sorry, this is not a minimization t, but this is going to minimization with respect to r, with respect to r. So you get x0 hat and r hat. So your fitted equation is going to be x predicted, so xi hat is going to be x0 hat into r cap into ti. So this is your fitted values. So these are your fitted values. This is the work which is, since it is a non-linear regression, non-linear function, that is why it's called as a non-linear regression. So in multiple linear regression, you have considered a linear model where you have seen that you have probably considered something like this beta 1 xi plus error, which is called as a simple linear regression. Then what you have done there? You have done there yi minus beta naught minus beta 1 xi whole square I is equal to 1 to, and you have performed this minimization with respect to beta 0 and beta 1, and then you know how to write it in matrix form and everything. And in R you have used it as a lm function. Lm, this is going to give you the fitted of the linear regression model. I'm assuming that it is done for you. Well, okay, so this is what we have learned about multiple linear regression. Now, is it getting close to the actual mean, which we have already learned about it, which we know here because we have simulated it, right? So, what is the actual mean? T x0 txp of r comma t. Let me call is equal to, say I'm using, say, blue color, and 2, and lty is equal to 2, right? Let me just check out. X0 is already given value. It should not go that much beyond. This is the actual plot. This is the plot. This is the data plot. This is the summary of this fit. X0 hat and R hat. This is going to be the right RT hat. And this is the line, and we see that yes, I think some other values got stored there. So as we understand that they get a almost very close match with the estimated value. The reason is that here variance is little bit small, like that's why you get such a wonderful or almost like exact match. Had this variance be very high, this would have been a very much difference. Okay, so this particular concept that we have simulated from a population which we know, and we have fitted the model and we trace back that how close we got. In machine learning community, this is many times in fact misleading. Say for example you are talking about, you have learnt about multiple linear regression, so you have learnt about linear regression. Say for example I have this input data. So how we may get misguided in ML. How does it actually happen? Say, for example, you take the values, you take a sequence of values from 1 to 10, y is equal to 0.2. Okay? And suppose you consider v0 is equal to, and v0 is equal to say 1, and v1 is equal to say 0.5, and sigma is equal to say, for example, you take 1. Okay, and you simulate your y b0 plus b1 star x plus r norm n is equal to length of x, mean is equal to 0, and is equal to sigma. Let us first see what I have done by doing this. If we plot x comma y, PCH is equal to 19, call is equal to, say, gray color I can give. So this is the graph, no, not gray. Okay. So say for example, if your population variance is 0.1, as you see that from the data itself, you can understand that the population variance is small. So in a sense that if I having a regression model of this form, and we know that here epsilon follows normal 0 comma sigma square, right? Now this sigma square, this particular quantity sigma square, many people underestimate it. The sigma square, which is the population variance, population error, population variance of the error. So population itself has a standard deviation. Population itself has an error, right? And it has a variance. So when we estimate beta 0, b1, but at the same time we need to estimate sigma square also. So in principle, there is actually three parameters you are estimating by doing this: beta 0, beta 1, and sigma square as well. So there are three parameters being estimated. Now, your choice you're coming up with, should you go for a linear regression model? That is heavily dependent on this term sigma square. So that means if your population has a higher variance, then you may not even be able to identify that whether should we start our analysis with a linear regression or not. I'm again repeating. You have population, so and this is your, so 1 plus 0.5 xi plus epsilon I follows normal 0 comma sigma square. So you know this is your population. This is population regression line. Right? And this is your, suppose you are collecting a sample from here. If sigma square is low, you are able to understand that maybe starting with a linear regression is reasonable to consider. But your population is linear. However, sigma square high, you may not even able to trace back that I should start with a linear regression. So let us try to analyze this by means of a simulation. So if I am having a sigma square, so let me take 4, see, 2 comma 2, 4 plots. So here your sigma is small. Remember that I am simulating from linear regression model. Population line is linear. So population relationship is linear. So this is true because I am simulating from a linear population. Okay. So suppose that I am increasing now the population variance to 0.5 population standard deviation. You see that still you are able to make it. Okay, linear regression possibly could be an option. If I make it 1, more distorted, right? If I make it 2, here it here it seems that here it seems like you are not able to guess that should we start with a linear regression or something. If I make this sigma is equal to say 3, you tend to feel that it is probably a constant. There is no variation probably, or maybe you may thought of some kind of a local regression idea. Here probably you take something, here probably you take something, or here probably you take something. It can be some piecewise constant, it can be some piecewise polynomial, or it may be something, in fact, k nearest neighbor regression also, right? So as you see that when you know your population, here you know this is a very very fundamental idea. Not every current the traditional data science books will not have it. If you read Elemental Statistics, who are the inventor of many of these methods, like Dictionary and their ESL, statistical learning books, there you will find such kind of examples. Then you know your population well because you are simulating from a linear regression model your data. But still, the scatter plot is coming from there. You are not able to identify that given the data whether I should start with a linear regression model or adopt to some other methods. So that is why this population variance is a very very important factor. Means estimation is also equally important. I hope I am able to explain this that when there is a population scenario and there is a data scenario, based on the data we always try to approximate the population. So that we assume that population probably behaving following this rule. However, depending on the population variance, the data we are getting in our hand, not necessary that we will always be able to get hold of the actual population scenario. Okay, this is a very very critical idea. So by this, what I have done here, that I explained how we can solve differential equations with data. Then we have also learned how we can fit these differential equations. This is the solution of these differential equations and how we can fit this using the data. And this is the fit that we have already shown it over here. One is the true and one is the estimated, and these guys are getting close to each other, right? And similarly, the same exercise I have carried out for logistic model also, right? As you see that you when you know your truth, this is the truth. But based on this data, you got these estimates, right? So this is very important that as a mathematician we get adapted to the language of uncertainty because we are at least myself, probably I should say myself, I'm not should not generalize to everybody because we had been always prone to understand that uniqueness and existence and uniqueness, so there is only one guy who is going to do that job and we are going to have a unique solution. But when we are not adapted to the language of uncertainty, so here many of those, so that is the truth, but based on that data I got this estimated. So if I again simulate the data, I may get something different. But true is never ever going to change. So depending on the population variance, I my estimated graph is having going to have a deviation from the true one. However, in real life, you are never ever going to see this true line because we always collect data from the events from the natural processes or environmental processes or the financial movements, stock market data, those things, right? We never ever know how exactly they are working, but we can get a good estimate of this by employing uh, a, a judiciously employing some statistical method. The same thing I did for theta logistic growth equation. The same thing for compass, as you see. Now, this is something. This is a method which probably has not been uh, covered till now, as I saw the syllabus. Because so why let us just refresh it immediately that where we are sitting. So how this is being connected with your previous lectures. In your previous lectures, you have the data, right? You may have the data in this format that that you have a response yi and you have a predictors. Let's say p many predictors you are having, and you have an observation. So y1, y2, like this you have yn, and you have these values x11, x21, and xn1, like this. right? And x in P. And then you have fitted we assumed a linear relationship among them. So beta 0 plus beta 1 xi1 plus beta p xip plus epsilon I. This is a relationship you have assumed, then you have obtained either MLE or least square method. And you know that if epsilon are normally distributed, then both are equivalent. I will share another document where you can understand that in both the things, this guy is basically similar if we are in a normal distributed setup. Otherwise, they may not. So we come up with some. So then we minimize this. Then we minimize this yi minus beta naught minus summation bj x ij and ij is equal to 1 to p and its square. And you minimize it with respect to b0, beta 1 and beta p. And you get the estimates of this and you get the prediction model. Understood. This is what we have done. So in principle, if we think of in a one-dimensional case, you have the data scatter plots, right? And you fitted a curve. Say y is equal to f x beta is the parameter. This is the graph you have put it, and you call it as a f hat. F hat is equal to x beta is equal to f of x comma beta hat. So you estimate the beta by minimizing this yi minus fxi beta whole square and minimize it with respect to beta. So from this you get the beta hat, so you get this predicted equation f hat. Very nice. Now in many scenarios it happens that it's standard error or computing the confidence interval, it seems to be very important, right? Because you get only a single estimate of beta, right? So you get only a single estimate of beta. So uncertainty associated with beta cap must be estimated, right? What it does actually, right? If we want to estimate the uncertainty, what probably we can do? One of the very popular methods in machine learning community is called as a in particularly this is very useful when we have a data limited set or you cannot collect more data. So in that case it works like this. Say for example you have these are the data values that x1 y1 x2 y2 like this you have xn yn. From this you create a simple random sampling with replacement. What does it do? You have indices here 1 to n. So you randomly select n values from 1 to n, right? Say that you have got values like this, say 3, 2, 3, and like this, say 5, like this. So these are n values. So you create a new data. You create a new data. So 3 means is the third row. Here it will be x3, y3, x2, y2. This is x3, y3. This is x5, y5. You see that some of the rows are again being appeared over here because it is a with replacement. So once one value is being randomly chosen, that again that value is being returned over here. So that value we are again which number is coming, that row I'm selecting from here, putting it over here. This is the new data set. You call it as a bootstrap sample. This is the new sample we got called as a bootstrap sample. So again, perform this fitting exercise on this bootstrap sample. Okay, so this is going to give you another estimate of beta 10, right? Which is going to be maybe different than the original one. The original beta cap is this. Let me call it as a star. So this be another sample we have got, right? So the process that what we have done here, this whole process that we have done here, is repeat this process for 1,000 times. So that means you are going to have 1,000 many bootstrap sample. So in each of the bootstrap sample you perform in the model fitting. So you get beta 1,000 many bootstrap estimate of the beta, right? Now you get a grand estimate of the beta, which is overall of this, right? And you can also estimate the associated standard error. So 1 by 1,000 minus 1 beta star hat minus beta star hat bar, its whole square and its square root. It is called as a bootstrap standard error of beta hat, right? And once you got this one, then in fact based on this you can construct a CI as well. You can construct a confidence interval as well for the parameter, right? A typical choice may be that minus 1.96 approximately. So you basically rely on the normal distribution over here, right? So this is can be a typical confidence interval it can give you, right? It is called the bootstrap based confidence interval. Very important and very useful for applying in real data problems. Okay, and in particularly when as a statistician or a data scientist we are working in a biological related problems or dealing with ecological and environmental problems, then we have a data limited scenario. In that case, we do not have the flexibility to sample from the population, whereas we perform another sampling based on the sample that what we are already having in our hand. We're following the rule called as a simple random sampling with replacement. So what I have done over here, that how can you estimate the uncertainty estimation using bootstrap? So this is the logistic model, this is the simulation, this is the fix the parameters over here, and I simulated some values over here. So let me explain this to explicitly. Since the code will be there with you, I can find out this place in the document itself. Growth models, which section I want. After note, using bootstrapping. Right? So let me take the first line. This is going to be the logistic growth equation. Executed. And this is the first time I'm using NLS.control. That means I'm performing a nonlinear least square. So you can, how much maximum iteration you want, you can control that. These are for my simulation. Let me take var mf rho is equal to c1 comma 1, and you can plot p comma x. So this is actually the data that you got simulated, that the original data, that the scatter plot that you are having here, right? And then what we are doing it, we are considering it that we are performing the experiment. What I just explained, this is 1,000 times here it is written. I'm doing that same thing 500 times. So there will be 500 many estimates of x0, 500 estimate of r, 5000 estimates of, right? So this is bootstrap estimate of x0, right? Similarly for others also you can. So these are basically making the place for storing it. In the same procedure, I have done this over here, that I have the rows, number of rows. One is 10 row of data means it is going to give you 1 to 51. There are total 51 points are over here. So once I perform a sample, 1 is to n row of data, and replace is equal to true, then I performing actually found a permutation of the original data values. You see that? So it is a resample of the original number of rows. Another 51 values I get, but there will be repetition. For example, 31 has appeared twice, right? 35 has appeared here, here also 35 has appeared. If I do this thing once again, you see that the it started with 25, 36, 24. Now it is starting with 21, 6, 4. So you see that again you do it, again you do it. Such process has been carried out 500 times. So 500 such bootstrap sample has been generated. So these rows are being again arranged in that way. Okay. So this is precisely the procedure what has been we have carried out here. Let me execute this. Okay. So if you see that boot k, we get a lot of values of k. If we take a histogram of boot k, you see that this is going to be centered around these values, right? So these are the called as a bootstrap distribution of the parameters. Okay, so you can actually understand that whether these parameters have any kind of, whether these parameters there is some kind of a covariance or there is relationship between these parameters or not. Okay, so I need library car. You see that this is the wonderful plot, the scatter plot matrix that you can see. This says that x0r, this seems to be kind of a good correlations are there. However, r and k, they don't seem to be that much correlated, right? So whereas x0 and k, they also doesn't seem to be much related to each other. So these informations are very important because when you drawing inference for all the parameters, you have to consider their joint distributions, right? So for example, in multivariate scenarios or statisticians, you know, it is something called as a confidence ellipsoids, because it also takes care of the covariances associated with the parameters. And since you have already done the multiple linear regression, so you all know that if you write it down in matrix form, y is equal to x beta plus epsilon, n by 1, n by p plus 1, and this is p plus 1 by 1, and this is n by 1, and you minimize with respect to beta y minus x beta transpose and y minus x beta, then you know that the solution comes up with x transpose x whole inverse x transpose y. And you know that covariance between beta that this turns out to be sigma square x transpose x whole inverse. So that means the parameter estimates, these parameters, the estimators of the parameters, these guys are actually correlated, right? So, and this information must be taken into consideration when you are making joint inference for all the parameters. So that is why in a linear regression setup you know it very well. However, in non-linear regression setup, this is not that much clear, because in a typically non-linear regression scenarios, we we approximate the we approximate the variance, covariance matrix, everything using the Fisher information, which come from the second order derivatives of the Hessian matrix, inverse of the Hessian matrix, right? That's how we calculate the Fisher information, and from that we get the covariance of the parameters. However, if you for applications when you have a data limited scenario, definitely this method bootstrap is a very wonderful method which gives you an idea about the covariance, about the parameter relationships in your case, and accordingly you construct the confidence interval. So so when you say uncertainty, so I put this only for logistic equation, but definitely you can apply for your own method also. And this is the similar code you can adopt. This is the graph is also there, which you can see that. By the way, this graph got generated just by using this single line, last line. So now you can imagine that how powerful R Studio and R is, and doing machine learning methods, very reduced code, right? So then I have written a note on the some NLS function and wrote on some note on that, and I put some uh, real data analysis also over here, that how you can perform this task and perform the do the analysis for real data sets. Well, very good question. Just with the continuity, this is a very common understanding, common confusion, that it might happen that one or two rows this guy never comes into play. There is a probability, right? Because there is a probability, always a positive probability, that a particular row or one or two rows that never appears in any of the bootstrap sample. So that means the impact of that particular row is not included. It may be very highly influential row itself, whereas its contribution does not get included into my model selection or data fitting exercise. Very valid question, but fortunately, approximately, if you do this bootstrap process very large number of times, say 1,000 times or 2,000 times, approximately two-thirds of the times, the whole list of bootstrap sample, approximately two-thirds of the times, a particular row is going to be there. So every row in your data is going to be in approximately two-thirds of the, means approximately 66% of the data bootstrap data sets is going to have the that particular row. So the probability that it will not appear in any of these bootstrap sample is extremely small. So in your bootstrap distribution of the parameter, representation of all the rows are there with equal proportion. Okay, so there is a this is a it's a very small exercise. Theoretically, also you can prove it, that the probability that it is going to be a part of in one of the sample. So if you are having n values, so this you can take as a just take an exercise, that if you have n rows in the data and you have a bootstrap sample. So this is a bootstrap sample. So this one row, you take one row from here. This row is part of this bootstrap sample, has some approximate probability. This. So as this goes to eventually goes to E inverse, as your n basically is large. And what is E inverse? So exponential of -1, which is 0.633. Okay. So this is not present So present is approximately this. So 1 minus of approximately 63% of the, and what is 2 by 3? So they are very close, right? 0.03 difference. So approximately the probability that it is going to be in the part of the bootstrap sample is very high. It is almost 63%. So approximately two-thirds of the bootstrap sample, if from the original data you create say 1, 2 like this 1,000, and you have the sample say particular row, say the kth row. So kth row is going to be approximately 666 of them will contain the kth row, and this is same for all the rows. So that is a theoretical validation that why bootstrap actually works nicely. Okay, thanks for this question.